In the boundless tapestry of the cosmos, there exists a galaxy so overwhelmingly immense its sheer scale will challenge the very limits of your comprehension. This is no hyperbole, no sensationalized tale crafted for dramatic effect. This is the stark, profound truth of a cosmic leviathan reigning over 1 billion light-years distant, silently enduring in the spatial void, harboring more stars than you could count in 1 million lifetimes. If you're anything like me, you probably thought you had a grasp on just how colossal objects in space could be. You've seen the iconic images of Jupiter dwarfing our Earth. You've heard that our Sun could comfortably contain 1 million Earths within its fiery embrace. Perhaps you've even visualized our own Milky Way galaxy, a majestic spiral stretching 100,000 light-years from one edge to the other, a cosmic span that already feels impossibly vast. But all of that, every comparison, every mind-bending statistic you've ever encountered, dwindles into near insignificance when confronted with what astronomers have unearthed, lurking in a distant, forgotten corner of our universe. This discovery isn't just about big numbers. It's about pushing the boundaries of what we thought possible, forcing us to recalibrate our cosmic compass and reevaluate humanity's place in the grand design. If you're captivated by the most bizarre and astonishing phenomena our universe has to offer, please take a moment to like this video and subscribe to the channel. It genuinely helps us bring you more content like this, and signals that you want to continue this journey of cosmic exploration together. Now allow me to draw back the curtain. Our home, the Milky Way, is what scientists categorize as a barred spiral galaxy. It's characterized by those breathtaking, graceful arms, intricately woven from billions of stars, vast clouds of gas and cosmic dust, all spiraling majestically around a central bulge where a supermassive black hole holds silent gravitational sway. From one luminous edge to the other, our galaxy measures approximately 100,000 light-years across. This astonishing metric means that if you could somehow accelerate to the speed of light, the absolute fastest anything can travel within the known universe, it would still take you an unfathomable 100,000 years to traverse our galaxy from one side to the other. A number that even on its own is almost impossible for the human mind to grasp. 100,000 years. That's a timescale longer than the entire recorded history of modern humanity. It's longer than the period since our ancestors first learned to paint on cave walls, expressing their nascent consciousness. It's a span greater than all the civilizations that have ever risen and crumbled on Earth combined. Yet that is merely the breadth of our comparatively tiny corner of the cosmos. The Milky Way is a vibrant cosmic city home to an estimated 200 billion to 400 billion stars. Each one of these stellar furnaces could potentially host its own retinue of orbiting planets, with moons swirling around those planets, asteroids silently cruising through the void, and comets streaking across the interstellar expanse. Our Sun is but one humble star among these hundreds of billions nestled about 26,000 light-years from the galactic centre in a quiet, unassuming neighbourhood known as the Orion Arm. Our Sun, along with its family of planets, embarks on an epic journey around the galactic centre at an astonishing speed of roughly 800,000 kilometers per hour. Even at this breathtaking velocity, our solar system requires an incredible 250 million years to complete just one single orbit around the galactic core. Astronomers sometimes refer to this monumental duration as a cosmic year or a galactic year. To put that into perspective, during the entire epoch when dinosaurs roamed the Earth, our solar system hadn't even completed a full single revolution. The last time our Sun occupied this particular position in the galaxy, the most complex life forms on Earth were rudimentary marine organisms, simple creatures evolving in primordial oceans. Such is the immense mind-bending vastness even of our own galaxy. The space between individual stars within the Milky Way is almost unfathomably empty. Our nearest stellar neighbour, a small red dwarf star named Proxima Centauri, lies approximately 425 light-years away. This distance is so gargantuan that if you were to shrink our entire Sun down to the size of a single grain of sand, Proxima Centauri would be another identical grain of sand situated roughly 6.4 kilometers away. The immense expanse between them would be an absolute vacuum containing only the faintest wisps of gas and dust, and a few stray cosmic radiation particles. This profound emptiness is genuinely challenging for our minds to grasp. We humans inhabit a crowded planet encircled by billions of other individuals sharing space with countless other living organisms. We are accustomed to density, to proximity to a world teeming with life and matter, but venture beyond the confines of our solar system, and the vast, profound emptiness instantly becomes the universal rule. Stars are separated by abysses so immense that the probability of any two of them randomly colliding is infinitesimally small, effectively zero. Galaxies themselves can effortlessly pass right through one another like ghosts without any single star truly impacting another. Yet somehow, even within all that incredible void, there is still enough diffused matter to coalesce and form hundreds of billions of stars within our single galaxy alone. The gas and dust between stars might be incredibly diffuse, but spread across thousands of light years they accumulate into truly enormous quantities of raw material. New stars are actively being born right now within the colossal molecular clouds scattered throughout the Milky Way, in regions where gravity has patiently drawn enough gas together for nuclear fusion to dramatically ignite. Our galaxy is dynamically alive with the birth of stars even as older mature stars burn out their fuel and eventually die. When you gaze up at the night sky from an exceptionally dark location, that faint ethereal band of light gracefully arching overhead is in fact the combined luminescence of billions upon billions of distant stars within our own galaxy. Ancient civilizations in their poetic observations imagined it resembled spilled milk across the celestial dome, hence the evocative name Milky Way. For the vast majority of human history, we believed that was everything. We thought our galaxy was the entirety of the universe, the grand totality of all existence. Different cultures across millennia developed diverse and intricate explanations for that luminous band. The ancient Greeks spun tales of milk cascading from the breast of the goddess Hera. The Romans, with their pragmatic elegance, called it Via Lactea, the road of milk. In India, it was revered as the path souls traversed on their journey to the afterlife. Australian Aboriginal peoples envisioned it as a celestial river winding through the cosmic dreamtime. Across countless generations, humanity looked upon that luminous river of light and pondered its profound mystery. When the very first telescopes were painstakingly turned towards the Milky Way in the 17th century, early observers began to dimly perceive that the ethereal milky glow was actually an innumerable multitude of individual stars, each too faint and too densely packed to be resolved by the naked eye yet unveiled by the magnifying power of ground glass lenses. This was the nascent thrilling hint that our galaxy was far vaster and contained infinitely more stars than anyone had ever dared to imagine. It wasn't until the transformative 1920s that a brilliant astronomer named Edwin Hubble definitively proved that the hazy fuzzy patches previously observed through telescopes were in fact entire distinct galaxies unto themselves. Each of these celestial islands contained billions of its own stars, and each galaxy was situated at an unimaginably remote distance from our own. That monumental discovery radically reshaped everything we thought we knew about our modest place in the universe. Hubble meticulously made this groundbreaking discovery at the Mount Wilson Observatory in California, utilizing the largest telescope in the world at that time, a powerful reflector with a massive 2.5-meter diameter mirror. He was painstakingly observing a particular type of variable star known as a Cepheid variable, within what was then quaintly called the Andromeda Nebula. These remarkable stars pulsate regularly, varying in brightness over a predictable, consistent cycle, and by precisely measuring their apparent brightness and the rate of their pulsation, Hubble was able to calculate their exact distances. The results were nothing short of shattering. The Andromeda Nebula was not, as many astronomers had long assumed, a mere cloud of gas contained within our own galaxy. It was situated approximately 1,000,000 light-years away, lying far, far beyond the very fringes of the Milky Way. It was a completely separate independent galaxy, an island universe of stars in its own magnificent right. Our galaxy, the Milky Way, was definitively not the entirety of the universe. It was merely one galaxy among countless billions. Today we know that Hubble's initial distance estimate was in fact off by roughly a factor of 2. The Andromeda Galaxy is actually about 2 million light-years away from us, not 1 million. But the fundamental revolutionary conclusion remained resoundingly true. The universe was infinitely vaster than anyone had ever conceived, brimming with an uncountable multitude of galaxies, each containing billions upon billions of stars. As of today, we conservatively estimate that there are approximately 2 trillion galaxies within the observable universe. That's a staggering 2 followed by 12 zeros. Each and every one of those galaxies harbours billions or even trillions of its own stars. These numbers quickly become so astronomically large that they lose all practical meaning for our limited human brains. But here's where this story truly becomes gripping, pushing the narrative into a realm of escalating cosmic tension. Not all galaxies are created equal in the vast cosmic crucible. Some are diminutive dwarf galaxies, fragile stellar agglomerations with only a few billion stars. Others are majestic, sprawling spiral galaxies like our own Milky Way, or our massive nearest neighbour, the Andromeda Galaxy. And then at the absolute extreme end of this colossal scale reside the true titans, the undisputed monsters of the universe. These are galaxies so utterly gargantuan that they make our entire Milky Way appear no more significant than a stray dust motes drifting aimlessly in an empty cavernous warehouse. Galaxies manifest in a spectacular array of shapes and sizes, a testament to the diverse processes shaping the cosmos. The most prevalent type in the nearby universe are the elegant spiral galaxies, much like our own, distinguished by their characteristic pinwheel arms and flattened rotating disks. These galaxies are typically hotbeds of active star formation, with vibrant new stars continually being born within their gas-rich spiral arms. The breathtaking, intricate structure we observe is maintained by a delicate dance, a sublime balance between the rotational motion of the disk and the immense gravitational pull of all the matter contained within. Elliptical galaxies represent another primary morphological class. Unlike their spiral counterparts, these galaxies exhibit no particular internal structure. They vary in shape from nearly spherical to highly elongated ovals, and are predominantly composed of older reddish stars. Star formation within elliptical galaxies has largely ceased, as they have depleted most of their available gas supply. The most massive galaxies in the universe are almost exclusively ellipticals, gargantuan structures that have formed through the violent protracted mergers of numerous smaller galaxies over billions of years. Then there are irregular galaxies which defy any clear defined shape whatsoever. These chaotic forms are often the direct result of intense gravitational interactions with neighbouring galaxies, causing their delicate structures to be gravitationally stretched, distorted and torn asunder. The Magellanic Clouds visible from the southern hemisphere are classic examples of irregular galaxies actively being influenced and disrupted by the immense gravity of the Milky Way. Galaxies are far from randomly distributed throughout the cosmic expanse. Instead, they are meticulously organised into progressively larger, more intricate structures. Galaxy groups contain anywhere from a handful to a few dozen individual galaxies. Our own Milky Way is a member of the local group, which comprises approximately 80 known galaxies, including the Grand Andromeda and several dozen smaller dwarf galaxies. Galaxy clusters are even more massive aggregations containing hundreds to thousands of galaxies all gravitationally bound together. And the largest structures of all are the superclusters, truly colossal agglomerations of galaxy clusters that can span hundreds of millions of light years. These are the vast filamentary highways and knots of the cosmic web. The galaxy I want to tell you about today is one of those celestial behemoths, an undisputed cosmic monster. It bears a somewhat prosaic name, IC 1101, derived from its catalogue number, in a compendium of celestial objects compiled over a century ago. But do not let that dull designation deceive you. There is absolutely nothing boring or unremarkable about this cosmic titan. IC 1101 resides at the gravitational heart of a galaxy cluster known as Abell 2029, situated in the direction of the constellation Virgo as viewed from Earth. When astronomers meticulously aimed their most powerful telescopes at this region of the sky, they beheld a truly immense collection of galaxies, all gravitationally bound, dancing a slow, intricate ballet around a common centre of mass. And squarely at the very heart of that cluster, dominating everything around it, like a cosmic emperor on its throne, looms IC 1101. This single galaxy is estimated to boast a staggering diameter of approximately 4 to 6 million light years. Just let that profound number sink in for a moment. Our own Milky Way, which already seemed impossibly vast and incomprehensibly large, is only about 100,000 light years across. IC 1101 is therefore an astonishing 40 to 60 times larger than our entire galaxy. If you could hypothetically transplant IC 1101 to the current position of the Milky Way, it wouldn't merely engulf our home galaxy, it would swallow our entire local cosmic neighbourhood whole, a vast sphere of space stretching light years in every direction. The Andromeda Galaxy, our closest massive neighbour situated approximately 2.5 million light years away, would be comfortably nestled deep within the colossal embrace of IC 1101. The Triangulum Galaxy, another close neighbour, would similarly be consumed. All of the dozens of smaller dwarf galaxies that orbit us, places like the Large Magellanic Cloud and the Small Magellanic Cloud, would simply become insignificant, minute constituents of this Titan's sprawling, immense structure. But its sheer size is merely the beginning of what makes IC 1101 so utterly astonishing. This galaxy is estimated to contain an incomprehensible 100 trillion stars. 100 trillion our Milky Way by comparison may harbour at most 400 billion stars. This means IC 1101 possesses an astounding 250 times more stars than our own galaxy. If you were to embark on the impossible task of counting every single star within IC 1101, attempting to tally one star per second, without any pause whatsoever, it would take you over 3 million years just to reach the number 100 trillion. And that's assuming you never slept, never ate, and never rested in any conceivable way. This is a scale that utterly dwarfs even our most ambitious human endeavours. The saga of how we first came to glimpse this cosmic behemoth traces back to the year 1790, when a German-born British astronomer named William Herschel was systematically sweeping the night sky with his meticulously crafted telescope. Herschel was without question one of the greatest observational astronomers of his era. He had famously discovered the planet Uranus just a few years prior, and he dedicated a significant portion of his life to cataloguing thousands of celestial objects that no human eye had ever recorded before. On June 19th of that year, Herschel directed his telescope towards a region of the sky within the constellation Virgo and observed a faint, indistinct patch of light. He carefully noted its position, meticulously recorded his observation, and then moved on to the next celestial object on his list. At that momentous time, Herschel had no possible way of knowing what he was truly seeing. The technology simply did not exist to accurately measure the distance to this mysterious object, nor did the scientific understanding exist to recognize that it was in fact an entire galaxy, a distinct island universe entirely separate from our own. Herschel merely logged it as another nebula, one among many enigmatic cloud-like objects scattered across the celestial sphere. For more than a century, that faint nebulous patch remained a profound enigma. It was eventually christened EC 1101 when it was formally included in a comprehensive catalogue called the Index Catalogue, a significant expansion of earlier lists of celestial objects. Astronomers intermittently studied it when their burgeoning tools allowed, but without the necessary instruments to truly comprehend its fundamental nature. It remained just another entry in a lengthy scroll of cosmic oddities, a tantalizing mystery awaiting deeper insights. Everything profoundly shifted in the early 20th century as astronomers developed vastly superior telescopes and pioneered revolutionary new techniques for measuring cosmic distances. They made the stunning realization that IC 1101 was not, as previously thought, a mere cloud of gas contained within our own galaxy. It was an entirely separate galaxy situated at an almost unbelievably remote distance. The light we perceive from IC 1101 today began its epic journey from that galaxy over 1 billion years ago. It has traversed the immense cold void of space for more than 1,000 million years simply to reach the sensitive detectors of our telescopes. When that ancient light first embarked on its arduous voyage towards us, life on Earth was still predominantly comprised of single-celled organisms. Complex animal species had yet to evolve beyond rudimentary forms. Dinosaurs would not make their grand appearance for another several 100 million years. Every major event in the annals of human history, from the emergence of the very first civilizations to the invention of the telescope itself, unfolded while that primordial light was still relentlessly crossing the vast intergalactic expanse. As astronomers continued their painstaking studies of IC 1101, they began to unravel the profound mystery of why it had grown to such colossal proportions. This galaxy had not simply expanded to its monstrous size through ordinary gradual processes. It had become a true titan through an ongoing ballet of cosmic violence, a relentless process of galactic agglomeration that has unfolded over billions of years. IC 1101 is what scientists chillingly refer to as a cannibalistic galaxy. It has been and continues to be voraciously devouring other galaxies, assimilating their stars and gas into its own burgeoning mass. To truly grasp the concept of galactic cannibalism, you must shift your perspective and consider how gravity operates on the largest, most profound scales imaginable. Galaxies do not exist in serene isolation. They are intricately grouped into vast clusters, held together by their mutual gravitational attraction. Within these dense clusters, galaxies ceaselessly orbit one another, sometimes merely gliding past in close encounters, at other times engaging in direct cataclysmic collisions. When two galaxies approach each other in this cosmic dance, their immense gravitational fields begin to exert powerful tidal forces, distorting and reshaping their delicate forms. Stars are inexorably dragged out of their normal stable orbits. Gas and dust clouds are compressed and stretched, forming colossal tendrils reaching into space. If the galaxies are of similar size, they might embark on a protracted, complex merger over hundreds of millions of years, eventually coalescing into a single larger new galaxy. But if one galaxy is significantly more massive than the other, a different, more violent fate unfolds. The larger galaxy simply absorbs the smaller one, stripping away its stars and gas, adding all that captured matter to its own colossal bulk. This relentless process is precisely what has transpired with IC 1101 over billions of years of cosmic history. As the largest and most massive galaxy within its cluster, IC 1101 sits at the very gravitational nexus of everything surrounding it. Smaller galaxies that venture too close are inevitably ensnared by its colossal gravitational pull. They spiral inward slowly but surely, being torn apart and consumed over many millions of years. Each successive meal contributes to IC 1101 growing slightly larger, a little more massive, and even more gravitationally dominant. Scientists estimate that IC 1101 has undergone at least 76 major mergers throughout its long violent history. That's 76 separate instances where another substantial galaxy fell into this cosmic titan and was absorbed into its immense mass. And those are just the major mergers. Countless smaller dwarf galaxies have also been consumed stellar snacks so minuscule they barely registered as a full meal for this gargantuan predator. The compelling evidence for this cannibalistic history is unmistakably etched into the very structure of IC 1101 itself. When you observe a galaxy like our own Milky Way, you perceive a breathtaking spiral pattern, with elegant arms winding gracefully from the centre. These spiral arms are vibrant regions where stars are actively forming, where immense clouds of gas and dust are collapsing under gravity to give birth to new stellar nurseries. Spiral galaxies are rich in both gas and dust, the essential raw materials required for active star formation, and they exhibit a distinct flattened rotating disk shape. IC 1101 bears little resemblance to this. It is what astronomers classify as an elliptical galaxy, meaning it possesses a smooth, featureless oval-like appearance, completely devoid of any discernible spiral arms. Elliptical galaxies typically form when spiral galaxies violently merge together. The intense gravitational interactions and chaotic turbulence during the merger process utterly destroy the delicate spiral structures, violently mixing all the constituent stars together into a more randomized spherical or ellipsoidal distribution. The fact that IC 1 is an elliptical galaxy unequivocally tells us that it has undergone so many mergers that any initial spiral structure it might have once possessed has been completely and irrevocably erased. All those cataclysmic collisions, all that gravitational chaos has stirred its stars like ingredients being blended in a cosmic mixing bowl. What remains is this smooth, largely featureless titan, a stark testament to billions of years of relentless galactic consumption. But there's an even more remarkable, almost poignant aspect to IC 1101. Despite harbouring an astonishing 100 trillion stars, it is paradoxically a galaxy in the slow, inexorable process of dying. The vast majority of its constituent stars are ancient, profoundly old. Most of them are what astronomers refer to as red giants or yellow giants, venerable stellar objects that have already burned through most of their available nuclear fuel. Very few new stars are currently being born within the sprawling expanse of IC 1101. This might at first glance seem counterintuitive, given its immense star count and colossal mass. One might expect IC 1101 to be a vibrant hotspot of stellar activity, but recall just how massive it has become. Every time it voraciously consumed another galaxy, it also consumed that galaxy's supply of fresh star-forming gas. Gas is the indispensable fuel for the birth of new stars. Without a replenished supply of gas, new stars simply cannot be born. Over billions of years of relentless galactic cannibalism, IC 1101 has either utterly used up or violently expelled most of its available gas supply. The merger events themselves are often sufficiently violent to heat gas to extreme temperatures, causing it to expand and escape the galaxy entirely, or to compress it so rapidly that it all forms into stars simultaneously, in brief, intense bursts of activity. Either way, the ultimate outcome is a galaxy that has largely depleted its raw materials. What remains is a quiet, majestic giant slowly fading into the cosmic night. Its existing stars will continue to shine for billions of years yet, but as they ultimately burn out and perish, there will be no new generations to replace them. IC 1101 is akin to an ancient empire that has conquered all its neighbours, but has no heirs to inherit its vast legacy. It is colossal, powerful, and utterly magnificent, but it is also nearing the twilight of its active life. Nestled right at the very heart of IC 1101 lies something even more astonishing than the galaxy itself. Residing at the gravitational core of this cosmic titan is one of the largest supermassive black holes known in the entire observable universe. Every large galaxy is understood to harbour a supermassive black hole at its core. Our own Milky Way, for instance, hosts one named Sagittarius A, which contains approximately 4 million times the mass of our Sun. The black hole at the centre of the Andromeda Galaxy is even more prodigious, containing an estimated 100 million to 200 million solar masses. But the black hole at the heart of IC 1101 belongs to an entirely different, more extreme class. Scientists estimate that it contains anywhere from 40 billion to a staggering 100 billion times the mass of our Sun. To put this mind-boggling figure into stark perspective, this single black hole could possess a mass up to 25,000 times greater than the black hole at the very centre of our entire Milky Way galaxy. Let me attempt to help you truly comprehend the sheer magnitude of this mass. If you could somehow weigh the Earth, you would find it has a mass of approximately 6 sextillion kilograms, or 6 followed by 21 zeros. That number sounds utterly immense, and it is until you compare it to our Sun, which is approximately 330,000 times more massive than Earth. Our Sun is a rather ordinary star, neither exceptionally large nor particularly small by stellar standards. Now take the mass of the Sun and multiply it by 50 billion. That is the approximate mass estimated to be compressed into the supermassive black hole at the core of IC 1101. All of that mass is compressed into a region where escape becomes impossible, and the scale of that boundary grows with mass. The physical size of a black hole's event horizon is directly dependent on its mass. For a black hole possessing 50 billion solar masses, its event horizon would have a radius of approximately 150 billion kilometers. That number sounds gargantuan, and indeed it is. But remember, this is a region containing 50 billion times the mass of the Sun compressed into what is essentially a singular point at the centre. The event horizon is merely the demarcation line, the point of no return, beyond which escape becomes an absolute impossibility. To provide a clearer analogy, our entire solar system from the Sun out to the furthest reaches of Neptune's orbit spans roughly 9 billion kilometres in diameter. The event horizon of IC 1101's black hole is an astonishing 16 times larger than our entire solar system. If you were to hypothetically place this black hole at the position of our Sun, its event horizon would extend far beyond the orbit of Pluto, utterly engulfing everything we consider to be our cosmic home. What cataclysmic phenomena would unfold near such a monstrous black hole? The physics governing such extreme environments are profoundly bizarre and counterintuitive, pushing the very limits of our understanding. Time itself would dilate passing differently near the event horizon compared to distant regions. An individual falling towards the black hole would witness the external universe accelerate rapidly, a blur of cosmic history rushing past. Conversely, a distant observer would perceive the falling individual's journey as slowing down, seemingly freezing in time as they approach the event horizon. From an external perspective, they would appear to never truly cross the boundary. Inside the event horizon, all spatial directions inexorably lead towards the singularity at the centre. Space and time themselves are so grotesquely warped that the very concept of escape becomes utterly meaningless. The singularity, a theoretical point of infinite density, would ruthlessly tear apart anything that succumbed to its gravitational embrace, stretching it into thin, atom-thin strands through a process that physicists have chillingly dubbed spaghettification. But here's the truly remarkable, almost contradictory aspect. Despite its monstrous size and terrifying properties, the black hole at the heart of IC 1101 is currently relatively quiescent. It is not actively devouring vast quantities of matter. There is no brilliant accretion disk of superheated gas spiralling furiously around it. There are no powerful jets of matter blasting into space at near light speed characteristic of actively feeding black holes. The black hole is simply there waiting, but it has consumed most of the readily accessible matter within its immediate vicinity. This profound quietude is directly linked to the same phenomenon that has stifled IC 1101's ability to form new stars. Most of the galaxy's gas has either been used up or driven out, and without a steady inflow of gas falling towards the centre, the black hole has very little left to feast upon. Occasionally a stray star wanders too close and is mercilessly torn apart, providing a fleeting brief meal, but such events are exceedingly rare. The black hole, much like the galaxy that hosts it, is a resting giant immensely powerful yet largely dormant. Traces of the black hole's cataclysmic past activity still persist, providing tantalizing clues for astronomers. Scientists have detected a powerful radio source emanating from the core of IC 1101 catalogued as PKS 758.059. This intense radio emission originates from relativistic jets of matter, streams of particles accelerated to near the speed of light and violently ejected from the black hole's immediate vicinity. These formidable jets are energized by the black hole's rotation and its potent magnetic fields, and they are capable of carving out colossal cavities within the surrounding hot gas. X-ray telescope images distinctly reveal these immense cavities, which appear as gargantuan bubbles of extremely hot, incredibly tenuous gas vigorously inflated by the energy unleashed near the black hole. Some of these bubbles stretch millions of light years in diameter, silent testaments to past epochs when the black hole was far more dynamically active than it is today, the sheer energy required to inflate these bubbles is mind-boggling equivalent to the combined energy output of billions of stars over millions of years. This intricate dance of feedback between supermassive black holes and their host galaxies is one of the most vibrant and actively researched areas in modern astrophysics. Scientists now strongly believe that supermassive black holes play a crucial regulatory role in controlling galaxy growth and evolution. As gas streams inexorably towards the galactic centre, the black hole can unleash enough energy to dramatically heat that gas and forcefully expel it outwards, thereby preventing it from cooling and forming new stars. This creates a type of cosmic thermostat effect, which effectively dictates the ultimate size and characteristics of galaxies. In the specific case of IC 1101, this powerful feedback mechanism is likely a primary contributor to the galaxy's current quiescent state. The black hole has effectively helped to shut down star formation by heating the gas and preventing it from cooling and collapsing. The colossal galaxy and its equally colossal black hole have reached a peculiar symbiotic equilibrium. Each has profoundly shaped the other over billions of years of shared evolution. Black holes grow by voraciously consuming matter that falls into their gravitational maw. When galaxies merge, the supermassive black holes at their respective centres eventually find each other and coalesce. Throughout IC 1101's long and violent history of galactic cannibalism, its central black hole has been steadily accreting mass growing larger with each merger. Every galaxy that EC 1101 consumed also contributed its own central black hole, adding more fuel to the insatiable appetite of this growing monster. The process of two supermassive black holes merging is both mesmerizing and staggeringly violent. When two galaxies initially collide, their central black holes do not immediately find each other. They are separated by immense distances and encircled by billions of stars. But as the merger unfolds, gravitational friction with the surrounding stars causes the black holes to slowly spiral inward towards the centre of the combined galaxy. Eventually, the two black holes draw close enough to form a binary system orbiting each other in a tightly bound celestial dance. As they orbit, they radiate energy away in the form of gravitational waves, ripples in the fabric of space-time itself. These gravitational waves carry energy out of the binary system, causing their orbit to progressively shrink. The black holes spiral closer and closer, rotating faster and faster, until they ultimately coalesce in a catastrophic event that unleashes an enormous amount of energy. When two supermassive black holes finally merge, the gravitational waves they generate represent one of the most powerful and energetic events in the entire universe. The final merger itself releases more energy than all the stars in a typical galaxy combined, although the vast majority of this energy is in the form of gravitational waves rather than electromagnetic radiation light. These waves propagate outwards at the speed of light, stretching and compressing space-time as they pass through. We have only very recently developed the technology to directly detect gravitational waves. The first direct detection occurred in 2015 when the LIGO observatories measured waves from two stellar mass black holes merging approximately 1 billion light-years away from us. Since then, dozens of gravitational wave events have been observed, opening up an entirely new way to study the universe. Future gravitational wave detectors, such as the LISA mission, planned for space, will be capable of detecting the mergers of supermassive black holes. When LISA launches perhaps in the 2030s, it may actually be able to detect events akin to the mergers that forge the central black hole of IC 1101. We will literally be able to listen to the universe as colossal black holes collide and coalesce, adding a brand new sense to our astronomical toolkit. IC 1101's black hole has undergone dozens of such mergers throughout its long and tumultuous history. Each merger event added to the black hole's immense mass and altered its spin. This process of repeated merging also profoundly affected the surrounding galaxy, as the coalescing black holes violently ejected stars outwards through powerful gravitational interactions. This is likely a key reason why the core of IC 1101 is so astonishingly large, yet relatively dim. The repeated black hole mergers have effectively scoured stars out of the very centre, creating an unusual core configuration for a galaxy of this staggering size. That same black hole left fingerprints across the cluster signals we can still detect today. For a black hole containing 50 billion solar masses, its event horizon would stretch outwards approximately 150 billion kilometers. That's a distance equivalent to our Sun out to the very outer edge of our solar system, all contained within a region of space from which even light cannot escape. Surrounding this supermassive black hole, there is a prominent radio source that astronomers have catalogued as PKS 07580059. This powerful radio emission originates from jets of matter violently ejected outwards from the black hole's immediate vicinity at velocities approaching the speed of light. While the black hole may not be as actively feeding as it once was, it still occasionally flares up, unleashing colossal amounts of energy into the surrounding space. The presence of such a monstrous black hole at the heart of IC 1101 raises fascinating questions about intricate connection between galaxies and the powerful enigmatic monsters residing at their hearts. Scientists have discovered a robust relationship between the mass of a galaxy's central supermassive black hole and the physical properties of the galaxy itself. Larger galaxies consistently tend to host larger black holes, but which came first? Did the black holes form first and then grow the galaxies around them? Or did galaxies form first and then gradually build up their black holes over time? The prevailing answer now appears to be that they co-evolve intricately linked. Each profoundly influences the growth and evolution of the other. As IC 1101 consumed more and more galaxies, its central black hole also consumed the black holes from those galaxies. These two processes acted in tandem, creating a powerful feedback loop that produced both the largest known elliptical galaxy and one of the largest known black holes we observe today. The core of IC 1101 is also noteworthy for its sheer immense size. A detailed study conducted in 2017, utilizing advanced imagery from the Hubble Space Telescope, meticulously measured the galaxy's core and discovered that it spans nearly 14,000 light-years. To put this into astounding perspective, the central core of IC 1101 alone, not the entire galaxy but just its innermost region, is larger than most entire dwarf galaxies. This core by itself contains more stars than the total population of most galaxies in the universe, an unparalleled concentration of stellar mass. Now I want to take you on a deeper imaginative journey to help you truly grasp the unfathomable scales we're discussing. Imagine for a moment that you could somehow travel from one side of IC 1101 to the other. You would need to traverse an immense distance of approximately 4 to 6 million light-years. Remember, light itself travels at an astonishing speed of roughly 9.5 trillion kilometers every year. Even at that incomprehensible velocity, crossing IC 1101 would demand millions of years. But let's try another comparison grounded in human endeavour. The Voyager 1 probe, launched by NASA in 1977, is the fastest human-made object ever to depart our solar system. It is currently hurtling through space at a speed of about 61,000 kilometers per hour relative to the Sun. At that breakneck speed, Voyager 1 would still require an estimated 80,000 years just to reach the nearest star to our Sun, Proxima Centauri, which is only about 4 light-years away. To traverse our entire Milky Way galaxy at Voyager 1 speed would take roughly 2 billion years. And to cross the colossal expanse of IC 1101, you would need an astonishing 80 billion to 120 billion years. That is a span of time longer than the entire current age of the universe itself. Even with our fastest spacecraft traversing this single galaxy, would be an utterly impossible feat. Here's another way to contemplate its scale, a vivid comparison to bring the abstract numbers closer to home. If you were to metaphorically shrink our entire Milky Way galaxy down to the manageable size of a dinner plate, approximately 25 centimeters across, then IC 1101 would by the same scaling be the size of a large swimming pool. Our entire galaxy, with its hundreds of billions of stars, with its intricate spiral arms where we reside, would be but a tiny solitary plate floating in a vast, profound sea. Or consider this truly ancient light. the light from IC 1101 has journeyed for over 1 billion years to finally reach our telescopes. In all that unimaginable time, light has continuously radiated outwards from this galaxy in every conceivable direction. Every single second, IC 1101 radiates enough light to travel approximately 300,000 kilometers. Over that span of more than 1 billion years, that light has covered a staggering distance of 1 billion light years, which is roughly 9.5 quintillion kilometers, 9.5 followed by 18 zeros. And now, after this epic journey, those ancient photons have only just begun to arrive at our telescope's primordial light that departed its home galaxy when Earth was still in the earliest, most nascent stages of complex life. The breathtaking discovery and subsequent study of IC 1101 would have been utterly impossible without the monumental advancements in telescope technology. In the nascent days of astronomy, telescopes were fundamentally limited by the physical size of their lenses and mirrors. Larger telescopes could naturally gather more light, enabling astronomers to discern fainter, more distant objects. But there were practical engineering limitations to how large you could construct a telescope on the ground. The Earth's atmosphere also presented a significant impediment. The terrestrial atmosphere is in perpetual motion, shimmering and distorting, which is precisely why stars appear to twinkle. This atmospheric turbulence blurs the images that ground-based telescopes can capture, severely limiting the clarity with which they can resolve distant objects. For the greater part of the 20th century, astronomers could ascertain that IC 1101 existed and was indeed exceptionally large, but they lacked the sophisticated tools to meticulously study its intricate structure in detail. Everything dramatically changed with the launch of the Hubble Space Telescope in 1990. Orbiting far above the distorting effects of the atmosphere, Hubble became capable of capturing images with unparalleled clarity and resolution. In the decades since its launch, Hubble has observed IC 1101 multiple times, meticulously revealing intricate details about its vast core, its surrounding stellar halo, and its complex gravitational relationship with other galaxies within its cluster. More recently, astronomers have employed a diverse array of telescopes to study IC 1101 across the entire electromagnetic spectrum, observing at different wavelengths of light. Radio telescopes have successfully detected the powerful radiation emanating from its central black hole. X-ray telescopes have peered into the superheated gas that pervades the cluster surrounding it, painting a picture of its energetic environment. Infrared telescopes have penetrated through layers of cosmic dust to scrutinize the populations of stars deep within the galaxy. Each new observation, each different wavelength adds another crucial piece to our intricate understanding of this cosmic titan. But much remains unknown. The precise number of stars within IC 1101 remains uncertain, as counting individual stars in such a distant galaxy is an incredibly difficult endeavour. The exact physical size of the galaxy is also ambiguous, as it depends on how one defines its outer boundary. Galaxies don't possess sharp, definitive edges, but rather gradually fade into the profound darkness of intergalactic space. The mass of the central black hole is known only approximately as measuring black hole masses. At such extreme distances involves numerous complex assumptions and models. What we do know with certainty is that IC 1101 represents an astonishing upper limit on the scale that galaxies can attain. It is possible, though highly improbable, that slightly larger galaxies might be awaiting discovery lurking in some unobserved corner of the universe. In fact, in 2022, astronomers announced the discovery of a galaxy named Alcyonius, whose radio lobes extend an astonishing 16 million light-years across. But Alcyonius is a peculiar special case. Its gargantuan size primarily arises from the colossal jets of matter violently blasted out from its central black hole, rather than from its ordinary stars and galactic matter. When it comes to the galaxy itself, the actual collection of stars, gas, and dark matter that constitutes its physical entity, IC 1101 steadfastly remains one of the largest, if not the largest, galaxies ever found. It occupies the extreme upper end of the galactic size distribution, a true monster among giants. The narrative of IC 1101 also imparts a profound lesson about the fundamental nature of the universe and the grand sweep of cosmic time. Galaxies do not spontaneously spring into existence in their final form. They undergo billions of years of dynamic evolution through processes of accretion and violent mergers. Smaller galaxies initially coalesce from the collapse of primordial gas clouds. These smaller galaxies then relentlessly merge with one another to form progressively larger galaxies. Even larger galaxies then merge to form even more colossal ones. And so it continues, with the largest galaxies growing even more massive by voraciously consuming their smaller, less fortunate neighbours. This hierarchical process of structure formation is one of the foundational tenets of modern cosmology. The universe meticulously builds everything from the bottom up, starting small and growing large through countless mergers over cosmic eons. IC 1101 is simply the most extreme, awe-inspiring example of this hierarchical process that we have encountered to date. It has had billions of years and a perfectly advantageous location at the centre of a rich galaxy cluster to swell to its incredible proportions. But even growth cannot continue indefinitely. IC 1101 has already consumed most of the galaxies that were sufficiently close to fall into its gravitational well. The remaining galaxies are either too distant or moving too rapidly to be easily captured. The surrounding cluster itself is gradually being stretched apart by the relentless expansion of the universe, carrying potential victims ever further beyond IC 1101's gravitational reach. Simultaneously, the broader universe is undergoing profound changes that will ultimately affect every single galaxy, including this colossal one. Space itself is expanding, and not merely expanding, but accelerating in its expansion. This terrifying acceleration is driven by what scientists enigmatically refer to as dark energy, a mysterious force that accounts for approximately 68% of the total energy density in the universe, yet whose fundamental nature we scarcely comprehend at all. Allow me to elaborate a little further on dark energy, for it is one of the most compelling and perplexing discoveries in all of science. For the majority of the 20th century, astronomers widely assumed that the expansion of the universe was gradually decelerating. This seemed logically sound. Everything in the universe exerts a gravitational pull on everything else. You would naturally expect all that combined gravity to act as a cosmic brake, slowly slowing down the expansion that began with the Big Bang. Then, in 1998, two independent teams of astronomers made a shocking revolutionary discovery. They were meticulously measuring the expansion rate of the universe by observing distant supernovae, utilizing them as standard candles to precisely calculate cosmic distances. What they found was utterly unexpected and paradigm-shifting. The universe was not decelerating. It was in fact accelerating. Distant galaxies were receding from us at an ever-increasing pace, much faster than closer galaxies. And the rate of this expansion was accelerating over time. This discovery was so profoundly unexpected that astronomers initially feared they had made a grievous error. But as more and more data poured in from additional supernovae and from other independent observations, the results steadfastly held true. Something was actively pushing the universe apart, counteracting gravity, and causing space itself to expand at an ever-increasing rate. Scientists christened this mysterious force dark energy. While the name tells us very little about its true nature, we know that dark energy accounts for approximately 68% of the total energy in the universe. We know that it acts as a kind of anti-gravity, pushing space apart rather than pulling it together. We know that its effects become increasingly dominant over time as the universe expands and ordinary matter becomes more diffuse, but we remain utterly ignorant of what dark energy is fundamentally made of, where it originates, or why it possesses such an immense power. It could potentially be an intrinsic property of empty space itself, a phenomenon known as the cosmological constant that Albert Einstein once proposed and later famously called his biggest blunder. It could be a novel type of energy field permeating the universe. It could even be a radical indication that our current understanding of gravity is fundamentally incomplete, and requires profound revision. What we do know is that dark energy is dramatically reshaping the long-term future of the universe. As space expands faster and faster, distant objects will recede from us at ever-increasing speeds. There is a firm limit to how fast light can travel, but there is no such limit to how rapidly space itself can expand. Eventually, objects will be swept away from us by the expansion of space faster than their light can reach us. When that occurs, they will disappear behind a cosmic horizon forever lost and beyond our reach. For IC 1101, this cosmic reality implies that its days of growth through galactic cannibalism are definitively finite. Eventually, there will be no more galaxies within its gravitational reach for it to consume. It will become increasingly isolated, a lonely titan drifting in an ever-emptying universe, watching every other galaxy outside its local cluster fade irrevocably from view. In fact, let me paint an even more detailed, poignant picture of this distant future. Recall that IC 1101 is located within the Abell 2029 galaxy cluster, surrounded by hundreds of other galaxies. These galaxies are gravitationally bound, orbiting around their common centre of mass. For now, gravity is sufficiently strong to hold the cluster together, staunchly resisting the relentless expansion of space. But in approximately 100 billion years, the cosmic expansion will accelerate to such an extent that galaxies beyond our local supercluster will begin to disappear behind the cosmological horizon. From the perspective of an observer within IC 1101, the night sky will gradually begin to empty. Distant galaxy clusters will progressively dim and then vanish from sight. Their ancient light will no longer be able to traverse the ever-expanding void. The observable universe, currently teeming with an estimated 2 trillion galaxies, will inexorably shrink and contract. Within the Abell 2029 cluster itself, things will remain more dynamic for a while longer. The galaxies there are close enough and sufficiently tightly bound that they will remain coalesced, even as the larger universe empties out. Over the next few billion years, these galaxies will continue to interact, merge and evolve. IC 1101 may still manage to consume a few more victims, growing slightly larger, even as the rest of the universe drifts away. But ultimately, even the galaxies within the cluster will eventually merge with one another. The same processes that built IC 1101 will continue to draw the remaining galaxies towards the centre, where they will be absorbed into an even larger combined structure. In the very long term, perhaps over several hundred billion years, all the galaxies within the Abell 2029 cluster could potentially merge into a single colossal supergalaxy, even more massive than IC 1101 is today. However, by that unimaginably distant epoch, the universe beyond the cluster would be fundamentally empty. No more light from distant objects would reach the cluster. The night sky, were any observers still present, would display only the stars of the local merged galaxy against an absolute profound blackness. The rest of the universe would have slipped beyond the horizon, forever inaccessible and unknowable. This is the ultimate isolation awaiting IC 1101 and every other bound structure in the universe, severed from everything else by the ceaseless accelerating expansion of space. Each island of matter will be left alone with itself as the cosmic eons unfold. But even this profound isolation is not IC 1101's ultimate fate. What happens to a galaxy in a universe that is slowly, inexorably decaying towards heat death? The answer is at once both magnificent and melancholic. Over the next 100 trillion years, the stars within IC 1101 will slowly, systematically flicker out. The most massive blue giant stars would have long since vanished, exploding in spectacular supernovae or collapsing into black holes. Medium-sized stars like our own sun will swell into luminous red giants, shedding their outer layers into breathtaking planetary nebulae, and then gracefully fade into dim, compact white dwarfs. Even the smallest, longest-lived stars, the ubiquitous red dwarfs that burn their nuclear fuel at such a leisurely pace they can shine for trillions of years, will eventually exhaust their hydrogen fuel and plunge into eternal darkness. Let me delve into more specific detail about this profound stellar demise, because the timescales involved are truly mind-bending. The most massive stars within IC 1101, the blue giants and supergiants, lived fast and died young. They consumed their nuclear fuel in mere millions of years before erupting in cataclysmic supernovae. Any blue giants that IC 1101 ever possessed would have burned out billions of years ago. The galaxy today is dominated by older, smaller, much longer-lived stars. Sun-like stars have lifespans of approximately 10 billion years. Our own Sun is about halfway through its life, with about 5 billion years remaining, before it expands into a red giant and eventually becomes a white dwarf. Within IC 1101, many Sun-like stars would have already completed this process, leaving behind their white dwarf remnants. Other such stars are still shining, but over the next few billion years they too will exhaust their fuel. But the most numerous stars in any galaxy are the red dwarfs. These tiny low-mass stars possess only a fraction of the Sun's mass. Red dwarfs burn their nuclear fuel so incredibly slowly that they can shine for trillions of years. A red dwarf born at the same time as our Sun will still be shining brightly long after our Sun has become a cold, dark white dwarf. Within IC 1101, with its 100 trillion stars, there are countless red dwarfs. These tiny dim stars will be the very last stars to flicker out. For trillions of years after the larger stars have died, the red dwarfs will continue to burn, providing the only faint light in a progressively darkening galaxy. But even red dwarfs have their limits. The smallest red dwarfs, perhaps 8% of the Sun's mass, might burn for up to 10 trillion years. That is approximately 700 times the current age of the universe. But eventually even they will exhaust their hydrogen fuel and fade irrevocably into the cosmic darkness. Scientists estimate that effective star formation across the universe will largely cease in approximately 100 trillion years. By that point, the gas and dust necessary to create new stars will have either been entirely used up or dispersed too thinly to collapse under gravity. No new stars will be born to replace the dying ones. The era of starlight will come to a definitive end. Every single one of IC 1101's 100 trillion stars will slowly individually dim and die. The galaxy will fade over timescales that make the current age of the universe seem like a mere blink of an eye. Where once stood a brilliant ocean of starlight, there will eventually be nothing but the cold, dark remnants of dead stars, white dwarfs, neutron stars and black holes, all drifting through an ever-expanding, ever-cooling void. The universe at this stage will be a dark place, but not an empty one. All those stellar remnants, all those white dwarfs, neutron stars and black holes will still persist. They will orbit the merged remnant of what was once IC 1101 and its companion galaxies within its cluster. The galaxy will be a ghost of its former self, filled with the inert corpses of stars rather than by vibrant burning suns. But even this is not the absolute end. Over even longer timescales measured in numbers of years, with so many zeros that writing them out would fill entire pages. Even these stellar corpses will slowly decay. White dwarfs will gradually cool until they become black dwarfs, theoretical objects that no longer emit any light or heat whatsoever. This cooling process takes an almost unimaginably vast amount of time. A white dwarf will cool to near absolute zero only after approximately 10 to 15 years, or about 1,000,000 trillion years. That's roughly 100,000 times the current age of the universe. Neutron stars too may eventually decay as their fundamental constituent particles gradually break down. We're not entirely certain about this, as it depends on whether protons, the building blocks of atomic nuclei, are truly stable, or if they too will eventually decay. Some theories of particle physics predict that protons will eventually decay with a half-life of around 10 or 34 years, or even longer. If this proves to be true, then over inconceivably long timescales, even the matter that makes up neutron stars and white dwarfs and planets and everything else will slowly inexorably disintegrate into radiation, and black holes, including the colossal monster at the heart of IC 1101, will gradually evaporate through a quantum process known as Hawking radiation. Stephen Hawking famously discovered that black holes are not truly black. They slowly leak particles and radiation over colossal durations, gradually shrinking as they do so. This occurs due to quantum mechanical effects near the event horizon. In the strange world of quantum physics, virtual particle-antiparticle pairs are constantly popping into and out of existence. Near a black hole's event horizon, one member of such a pair can fall into the black hole while the other escapes into space. Over time, this process drains energy from the black hole, causing it to shrink. The rate of Hawking radiation is incredibly slow for large black holes. A black hole with the mass of our Sun would take approximately 10^67 years to evaporate. That's a 1 followed by 67 zeros. But the supermassive black hole at the centre of IC 1101 is billions of times more massive than the Sun, and the time it will take for it to evaporate is correspondingly longer. A black hole containing 50 billion solar masses would take an astonishing 10^100 years to evaporate, or even longer. That's a Google years, a 1 followed by 100 zeros. To write that number out in full would require more paper than exists on Earth. It is a time frame so unimaginably vast that everything we have discussed so far, from the Big Bang to the death of the very last stars, doesn't even register as a rounding error by comparison. But even this timescale is not infinite. Eventually, trillions upon trillions upon trillions of years from now, even the supermassive black hole at the heart of IC 1101 will radiate away its final bit of energy and vanish from the universe in one final climactic burst of Hawking radiation. When that utterly final event eventually occurs, nothing of IC 1101 will remain. No stars, no black holes, no remnants at all. Only the dispersed particles and radiation that once comprised a galaxy spreading outwards into an ever-expanding, ever-cooling, ever-darkening universe. The largest galaxy we've ever found will follow the same ultimate path as every other structure in the universe, dissolving into the endless night. This profound vision of the far future might seem bleak, yet I find something strangely beautiful and deeply moving about it. IC 1101 exists right now in this incredibly brief cosmic historical moment when stars still brilliantly shine and galaxies still glow with magnificent splendour. It has existed for billions of years, and it will continue to endure for billions more. In the grand, sweeping river of cosmic time, the epoch of stars and galaxies is but a fleeting phase, a brief effervescent bloom of complexity nestled between the fiery chaos of the early universe and the cold, profound emptiness of the distant future. We as conscious beings are incredibly fortunate to exist within this vibrant, blooming era. We are privileged to have evolved intelligence, to have meticulously crafted telescopes, and to have pointed them with insatiable curiosity towards the heavens. We are fortunate enough to have uncovered IC 1101 and to have grasped, at least in part, what it is and how it came to be. In the entire expansive history of the universe, stretching from the monumental Big Bang to the final inevitable heat death, this fleeting moment right now is singularly special. It is the precise moment when the universe has developed the astonishing capacity to observe itself, to ponder its own origins, and to ask profound questions about its very existence. And what we behold when we gaze upon IC 1101 is the largest scale to which the universe has ever assembled matter into organised self-gravitating structures. We witness billions of years of cosmic history indelibly written in the light of its stars. We perceive the culmination of countless galactic mergers, innumerable collisions, and endless ballet of gravitational violence that has somehow forged something truly magnificent. We see a monster, yes, but also a monument to the relentless forces that shape our universe and to the intricate processes that have built complexity from the very first atoms. Let me draw our perspective back a little closer to home for a moment. Our own Milky Way galaxy is far from immune to the same powerful forces that have sculpted IC 1101. We too are actively engaged in the grand cosmic dance of galactic interaction and merger. Right now, even as you absorb these words, our galaxy is in the ongoing process of voraciously consuming several smaller dwarf galaxies. The Canis Major dwarf galaxy, for instance, is currently being torn apart and slowly absorbed into the Milky Way's burgeoning mass. The Sagittarius dwarf spheroidal galaxy is being gravitationally stretched and distorted by our immense gravitational pull. Streams of stars from past victims can be intricately traced across our night sky, ghostly reminders of galaxies that once existed as distinct independent entities. And in the not-so-distant cosmic future, an even more dramatic event awaits us. The Andromeda Galaxy, our closest massive galactic neighbour, is inexorably hurtling towards us on a collision course. Scientists have long held the belief that in approximately 4 to 5 billion years, the Milky Way and Andromeda will inevitably collide and eventually merge into a single, much larger galaxy, often affectionately nicknamed Milkomeda. Recent groundbreaking research, however, has introduced a degree of fascinating uncertainty into this dramatic prediction. New studies utilising refined data from the Gaia spacecraft and the Hubble Space Telescope suggest that the collision might not be as definitively certain as we once thought. When scientists meticulously factor in the complex gravitational influence of other nearby galaxies, such as the Large Magellanic Cloud and the Triangulum Galaxy, the probability of a direct head-on collision and subsequent merger diminishes significantly. Some advanced simulations now indicate only about a 50% chance of a full-scale merger occurring within the next 10 billion years, but regardless of whether it happens in 4 billion years or 10 billion years, or perhaps not at all, the process itself vividly illustrates the very same fundamental forces that built IC 1101. Galaxies interact, merge and consume one another. It is a universal fundamental law of the cosmos. Even our quiet, unassuming corner of the universe is actively participating in this colossal cosmic competition. If the merger does indeed occur, the outcome will be spectacularly dramatic, at least on cosmic timescales. The collision itself will not be as violent as you might imagine. Individual stars are separated by such immense distances that the probability of any two stars actually colliding is infinitesimally small, effectively zero. But the gravitational effects will be profoundly dramatic. The delicate spiral structures of both galaxies will be utterly destroyed. Immense clouds of gas will be compressed, triggering colossal bursts of star formation, igniting new suns across the tumultuous expanse. The two supermassive black holes at the heart of each galaxy will eventually find each other and merge, releasing a torrent of gravitational waves that will ripple across the universe. Over billions of years, the initial chaos will slowly subside. What was once the Milky Way and what was once Andromeda will coalesce into a single, vast elliptical galaxy, very much resembling IC 1101 in form, though significantly smaller in scale. Future astronomers, if any remain, might look back at ancient records and marvel that their smooth, featureless home galaxy was once two beautiful spiral galaxies dancing in the void. By that distant epoch, of course, Earth itself will be long gone. Our Sun is projected to expand into a red giant in approximately 5 billion years, swelling to a size that could engulf our planet. Whether humanity will have survived until then, whether we will have spread to other star systems, whether intelligence in any form will still exist in the universe, these are questions we cannot answer. But the story of ICL 1101 serves as a profound reminder that the universe operates on timescales that dwarf individual lives, individual civilizations, and even individual planets. I want to return to the question of what ICL 1101 tells us about our own place in the universe. When you gaze up at the night sky, you might feel a profound sense of insignificance. You might feel utterly tiny and inconsequential in the face of such overwhelming immensity. But I believe the very existence of IC 1101 actually imparts something deeply hopeful about our precarious situation. First, consider the astonishing fact that we are even able to know about IC 1101, a galaxy situated over 1 billion light-years away containing 100 trillion stars, and we have managed to decipher its immense size, understand how it formed, and even uncover the monstrous entity residing at its core. That in itself is utterly remarkable. Human beings residing on a small rocky planet orbiting an ordinary star in an unremarkable part of an average spiral galaxy have somehow evolved the cognitive capacity to comprehend objects so distant that their light departed before complex life even existed on Earth. This capacity for understanding is far from trivial. It is a profound testament to consciousness. In a universe composed of seemingly inert matter and energy of particles blindly bouncing according to the immutable laws of physics, somehow here on Earth, consciousness has miraculously emerged. Minds capable of wondering, of questioning, of investigating, and of learning. Whatever we are, we're a part of the universe that has awakened and begun to inquire about itself. Second, consider that IC 1101, no matter how utterly massive, is fundamentally composed of the exact same matter as we are. The stars within IC 1101 are thermonuclear reactors just like our Sun. They fuse hydrogen into helium and heavier elements precisely as stars do everywhere else in the cosmos. The atoms within those distant stars are the very same types of atoms that constitute our own bodies: carbon, oxygen, nitrogen, iron. All of them forged in the fiery hearts of stars somewhere, sometime in the universe. Just as the atoms in our own bodies were forged in stars that exploded before our Sun was even born, there is a profound continuum here, an unbreakable connection between us and everything else in the universe. We are not separate observers of the cosmos, we are inextricably a part of it. The same cosmic processes that meticulously built IC 1101 also painstakingly built us. The same atoms that glow in distant galaxies also sparkle in our eyes. We are not external spectators to the universe. We are the universe itself observing itself from within. Third, consider the profound implications that galaxies like IC 1101 are even capable of existing. The universe did not have to be this way. Had the fundamental physical constants been even slightly different, had gravity been a little stronger, or the nuclear forces a little weaker, stars and galaxies might never have formed at all. The universe could have either collapsed back in on itself shortly after the Big Bang, or expanded so rapidly that matter never coalesced into any structures. Instead, we inhabit a universe where the laws of physics are exquisitely tuned, allowing for the magnificent formation of stars, planets, galaxies, life, and intelligence. IC 1101 stands as a monumental testament to what is possible in such a universe. It is irrefutable evidence that matter and energy governed by simple physical rules over billions of years can organize themselves into structures of astonishing complexity and breathtaking beauty. If the universe can create IC 1101, what else then might it be capable of creating? What other wonders exist out there that we have yet to discover or even conceive? This brings me to the final point I wish to make about IC 1101 and about our ongoing journey to comprehend the universe. Every discovery we make, every galaxy we meticulously study, every black hole we carefully observe, expands our collective consciousness of what is possible. Just a few centuries ago, humanity arrogantly believed that Earth was the absolute center of everything. Then we learned that we orbit the Sun. Then we learned that the Sun is but one star among hundreds of billions in our galaxy. Then we learned that our galaxy is just one among trillions of galaxies. Each successive step has made us smaller in one sense, but it has also made the universe exponentially grander, more fascinating, and infinitely more worthy of profound awe. IC 1101 represents yet another monumental step in that journey. It reveals to us that the universe can construct things far, far larger than we had ever dared to imagine. It challenges us to ceaselessly question, to continually look further, to relentlessly push back the boundaries of what we collectively know. And it poignantly reminds us that, however insignificant we may be on a cosmic scale, we are the ones asking the questions, we are the ones looking, we are the ones pushing that boundary. Faced with the staggering grandeur of IC 1101, we can either choose to feel small, or we can choose to feel profound awe. I, for one, choose awe. As we bring this extensive exploration of the largest galaxy ever discovered to a close, I wish to leave you with a final lingering image. Imagine yourself, if you can, adrift in the cold, silent expanse of space, somewhere near the outer fringes of IC 1101. Around you, in every conceivable direction, stars stretch into an apparent infinity. Not just hundreds, not thousands, not millions, but hundreds of trillions of stars. Each one of them a blazing sun. Each one potentially hosting its own retinue of planets. each one having shone for billions of years. You cannot discern the centre of the galaxy from this vantage point. It is too distant, obscured by countless veils of stellar dust and light. Nor can you perceive its ultimate edge. The galaxy seamlessly fades into the profound darkness of intergalactic space without any discernible sharp boundary. You're utterly lost in an ocean of light adrift within a structure so vast that traversing it would require millions of times longer than the entire existence of human civilization. And yet, from a small rocky planet situated over 1 billion light-years away, sentient beings who have existed for less than a fleeting cosmic moment have managed to discover that this place exists. They have meticulously measured its staggering size, estimated its unfathomable star count, and even located the colossal black hole residing at its very heart. They have painstakingly traced its tumultuous history back billions of years, and projected its long-term future trillions of years hence. They have placed it within the grand context of a vast expanding universe, and stand in silent, profound awe of its sheer magnificence. That perhaps is the most astonishing revelation of all. Not merely that IC1101 exists, but that we fragile and fleeting know that it exists. But before we fully conclude, I want to delve just a little deeper into some of the most fascinating aspects of what we've discussed. Because understanding IC1101 isn't simply about memorizing numbers and facts. It's about grasping the fundamental processes that have shaped everything in our universe, including ourselves. Let's speak more about the dynamic ballet that unfolds within a galactic merger. When I say that IC1101 has consumed dozens of other galaxies, it might sound like a simple, straightforward process akin to one object swallowing another whole. But the reality is far more intricate, far more violent, and infinitely more beautiful than any simplistic description can possibly capture. When two galaxies first begin to interact, the initial overture is a subtle gravitational dance. Even when the galaxies are separated by millions of light years, they can still profoundly feel each other's gravitational tug. This subtle gravity begins to very slightly warp and distort their delicate shapes. Stars that were peacefully orbiting their galactic centres begin to feel an unexpected pull from an alien direction. Clouds of gas that were drifting serenely begin to move in new, perturbed ways. As the galaxies draw closer, these effects become progressively more pronounced and dramatic. If you could view a galactic merger in fast-forward compressing millions of years into mere minutes, you would observe the galaxies stretching and distorting like warm taffy being pulled apart. Long ethereal streams of stars are violently pulled out from each galaxy, forming what astronomers call tidal tails. These ghostly tails can stretch for hundreds of thousands of light years into the cold, dark expanse of space, silent spectral ribbons marking the immense violence of the interaction. The first close approach is rarely the final definitive collision. Instead, the galaxies often merely glance past one another, their mutual gravity slowing them down. They then recede, moving away from each other into the void. But by now they are inextricably bound. Like dancers whose hands have clasped, they cannot escape each other's gravitational embrace. Over the next few 100 million years, they will oscillate back and forth, drawing progressively closer with each successive pass until they eventually coalesce completely. During this tumultuous process, a truly remarkable phenomenon often occurs. The abundant gas within both galaxies is violently compressed by the immense gravitational forces and by powerful shock waves. This compression triggers colossal bursts of star formation. New stars, billions of them, ignite in a blaze of glory, burning hot and brilliantly luminous. Astronomers term these dramatic events starbursts, and they can temporarily transform a merging galaxy into one of the brightest objects in its entire cosmic neighbourhood. In some mergers, so much gas is driven towards the centres of the galaxies that it falls into the waiting supermassive black holes residing there. This feeding frenzy causes the black holes to unleash colossal amounts of energy, shining as quasars that can be observed across billions of light years of space. The very centres of the merging galaxies blaze with the light of matter, being voraciously consumed by hungry black holes, utterly outshining all the stars in both galaxies combined. Eventually the intense chaos subsides. The two galaxies become one. The new combined galaxy is significantly larger than either of its progenitor galaxies, but it also looks fundamentally different. The elegant spiral arms that may have adorned the original galaxies are gone utterly destroyed by the gravitational violence of the merger. What remains is often an elliptical galaxy, smooth and largely featureless. Its stars orbit in a complex randomized tangle of different directions rather than in the orderly disk of a spiral. This is precisely what has happened to IC 1101 not just once, but dozens upon dozens of times. Each merger added more stars, more mass, more matter to its central black hole. Each merger erased more of any initial structure the galaxy might have possessed. Over billions of years of this relentless process, IC 1101 grew to become the ultimate monster we observe today. Scientists can actually trace some of the tangible evidence of these past merger events. When astronomers meticulously study the stars within IC 1101, they uncover distinct populations of stars with varying ages and chemical compositions. These different populations are like geological strata in rock. Each layer records a different epoch in the galaxy's long and tumultuous history. Some stars are exceptionally ancient, perhaps original members of the primordial galaxy that existed billions of years ago. Other stars are younger, formed during the intense starburst triggered by merger events. Still other stars bear distinctive chemical signatures that indicate they originally formed in entirely different galaxies. Alien stars now absorbed into IC 1101's colossal mass. The core of IC 1101 itself tells a profound story of its violent history. As I mentioned earlier, its core is staggeringly large, spanning nearly 14,000 light-years. But it is also unusually dim for its immense size. Scientists believe that this is because the repeated mergers and the activity of the central black hole have actually scoured stars out of the very centre. Here's what they hypothesize occurred. When two supermassive black holes merge, they first form a binary system orbiting each other. As they spiral closer, they dynamically interact with passing stars, violently flinging many of those stars outwards at tremendous speeds. This process, ominously known as gravitational scouring, can effectively empty out the very centre of the galaxy, creating a region with fewer stars than you would naturally expect. IC 1101 has undergone so many mergers that its core has been repeatedly scoured over and over again. The result is a massive core that is actually deficient in stars compared to what models would predict. Scientists estimate that hundreds of billions of solar masses of stars may have been violently ejected from the core throughout IC 1101's history. That is a colossal amount of stellar matter, more than the total mass of many normal galaxies violently pushed outwards into the halo, or even completely flung out of the galaxy. This type of cosmic detective work is what makes astronomy so utterly captivating. We cannot physically visit IC 1101. We cannot dispatch probes there or collect samples. All we possess is the faint light that eventually reaches our telescopes. But from that light, we can infer an astounding amount about what has transpired over billions of years. We can literally read the history of the universe written in photons. Now let me expand our perspective even further. IC 1101 is the largest galaxy of a specific type that we have found, but the universe is replete with extreme objects. Understanding where IC 1101 fits within the grand cosmic menagerie helps us appreciate just how truly remarkable it is. At one end of the galactic size spectrum are the dwarf galaxies. These are the smallest galaxies in the universe, containing anywhere from a few million to a few billion stars. Our own Milky Way is orbited by dozens of dwarf galaxies acting as its gravitational satellites. The smallest of these, like Segway 1, contain only about 1,000 stars. They are so incredibly faint that astronomers didn't even discover them until advanced sky surveys began in the 21st century. Dwarf galaxies play a crucial role in cosmic evolution. They are the fundamental building blocks from which larger galaxies are meticulously assembled. In the early universe, when the very first galaxies were forming, most of them were dwarf galaxies. These small galaxies then relentlessly merged with each other over billions of years, gradually building up the much larger galaxies we observe today. Every large galaxy, including the Milky Way, including IC1101, ultimately began as long-merged dwarf galaxies. Moving up the size scale, we find galaxies like the Large Magellanic Cloud, which orbits our Milky Way at a distance of about 160,000 light-years. The Large Magellanic Cloud contains approximately 30 billion stars and spans about 14,000 light-years in diameter. It is visibly discernible to the naked eye from the southern hemisphere as a faint ethereal cloud-like patch in the night sky. The Large Magellanic Cloud is in fact slowly but surely being absorbed by the Milky Way. Its gas is being stripped away, and it will eventually fully merge with our galaxy, adding its stars to our own collection. This is galactic cannibalism occurring right in our own cosmic backyard. Then we have galaxies similar in scale to our own Milky Way. Spiral galaxies of this approximate size typically contain 100 billion to 400 billion stars and span 100,000 to 200,000 light-years in diameter. They're abundant throughout the local universe. These magnificent pinwheels of gas and stars are regions where star formation continues even after billions of years. Our nearest large neighbour, the Andromeda Galaxy, is slightly more massive than the Milky Way. It contains approximately 1 trillion stars, perhaps 2 or 3 times the number of stars in our own galaxy. Andromeda's disk stretches about 220,000 light-years across, making it roughly twice the diameter of the Milky Way. If you venture to a dark sky location on a clear autumn night in the northern hemisphere, you can actually spot Andromeda with your unaided eye. It appears as a faint fuzzy patch, but what you're truly observing is the combined light of 1 trillion stars, the most distant object visible without a telescope. Beyond galaxies like Andromeda, we begin to step into the realm of the true giants. Some elliptical galaxies at the centres of galaxy clusters can contain several trillion stars and span hundreds of thousands of light-years in diameter. These galaxies were already considered among the largest objects in the universe, but they still don't approach the extreme scale of IC1101. IC1101 sits at the very apex of this hierarchical ladder. Its staggering diameter of 4 to 6 million light-years makes it approximately 20 to 30 times larger than the Andromeda Galaxy. Its 100 trillion stars would make it 100 times more populous than Andromeda. There are simply not many galaxies in the universe that can compare. There is one class of objects that might challenge IC1101's title of largest galaxy, and those are the giant radio galaxies. These are galaxies that possess immense jets of matter, violently blasting out from their central black holes. These relativistic jets can extend for millions of light-years into the intergalactic medium, making the overall structure far larger than any stellar agglomeration. The most extreme example discovered so far is a galaxy named Alcyoneus, announced in early 2022. Alcyoneus has radio lobes that stretch an astonishing 16 million light-years. That's roughly 3 times larger than IC1101, making it the largest known structure created by a single galaxy. But here's the critical distinction. The colossal size of Alcyoneus comes from its jets of matter, not from its stars. The galaxy itself, the collection of stars and normal matter, is quite ordinary. It contains only about 240 billion solar masses of stars, far less than IC1101. The jets are incredibly impressive, but they are essentially empty space containing very tenuous plasma and magnetic fields. They don't contain the trillions of stars that make IC1101 so utterly massive. So when we speak of the largest galaxy, we need to be precise about what we mean. If we mean the largest structure associated with a galaxy, then Alcyoneus and other giant radio galaxies take the prize. But if we mean the largest stellar agglomeration, the most massive collection of a galaxy's own luminous matter, then IC1101 remains the undisputed champion. There's another way to think about size that's worth considering. Instead of diameter, we could ask which galaxy has the greatest total mass. This turns out to be a complex question, because most of the galaxy's mass is not stars at all. It resides in something we call dark matter. Dark matter is one of the greatest enduring mysteries in modern physics. We cannot directly see it. It does not emit light, nor does it absorb light. It does not interact with ordinary matter except through the force of gravity. But we know it exists because galaxies rotate in ways that would be impossible if they contained only the matter we can visibly observe. Here's the problem. If you add up all the stars in a galaxy and calculate the gravitational force they should exert, you get a certain number. Then you measure how fast stars are rotating in the outer parts of the galaxy, which tells you how much gravity is actually present. The two numbers do not match. There is far more gravity than visible matter can account for. The solution, according to most astronomers, is that galaxies are encased within vast halos of dark matter that we cannot see, but which comprises the vast majority of the galaxy's total mass. In a typical spiral galaxy like the Milky Way, dark matter accounts for approximately 90% of the total mass. The star's gas and dust that we can actually observe are merely a tiny fraction of what is truly there. IC 1101 also possesses a dark matter halo, and it is correspondingly immense. Scientists estimate that the total mass of IC 1101, including its dark matter, could be as high as 100 trillion solar masses. That's roughly 100 times more massive than the Milky Way. This dark matter halo extends far beyond the visible stars of the galaxy. While the stellar mass of IC 1101 already spans 4 to 6 million light-years, the dark matter halo likely stretches out even further. Some models suggest it could reach for tens of millions of light-years, making the complete structure of IC 1101 and its surrounding environment truly staggering. Understanding dark matter is one of the greatest challenges confronting physics today. We know it's there because of its profound gravitational effects, but we have no idea what it is fundamentally made of. Many scientists believe it consists of some type of particle that does not interact with light or ordinary matter, a particle we have yet to directly detect. Massive experiments are underway around the world, meticulously designed to try and catch dark matter particles as they pass through Earth. So far, none have succeeded. The very existence of dark matter reveals to us that even our understanding of something as gargantuan as IC 1101 is far from complete. We can see the stars, we can measure the light. But 90% of what makes IC 1101 such a massive titan remains invisible to us, detectable only through its pervasive gravitational influence. There is still so much we do not know. Before we move on, I want to take a moment to explore the remarkable technology and human ingenuity that has enabled us to study objects as incredibly distant as IC 1101. It's easy to forget when we speak of a galaxy a billion light-years away just how challenging it is to learn anything about such remote objects. The very fact that we know so much about IC 1101 is a profound testament to centuries of scientific progress and the unwavering dedication of thousands of researchers. The story of how we observe distant galaxies begins with the development of the telescope itself. When Galileo first pointed a rudimentary telescope at the night sky in 1609, he could discern craters on the Moon and the moons of Jupiter. But distant galaxies were utterly invisible to him. They were simply too faint, their light too weak to be detected by the small lenses of early telescopes. Over the next 300 years, telescopes grew progressively larger and more sophisticated. Bigger mirrors could gather more light, allowing astronomers to see fainter objects. Better optics produced sharper images. By the time William Herschel discovered IC 1101 in 1790, he was using a telescope with a mirror about 45 centimeters in diameter, which was enormous by the standards of his time. Even so, all he could perceive was a faint fuzzy patch. He had no way of knowing what that patch truly was. The real breakthroughs arrived in the 20th century. Photography allowed astronomers to take long exposure images collecting light for many hours, rather than relying on the human eye's instantaneous perception. Spectroscopy enabled them to analyze the light from distant objects, splitting it into its constituent colors and inferring what elements were present and how fast objects were moving. Radio astronomy opened entirely new windows on the universe, detecting radiation invisible to the human eye. Each of these advancements revealed something new about IC 1101. Photographic plates showed it was far larger than he initially thought, extending much further than what visual observers could detect. Spectroscopy revealed that it was receding from us at a tremendous speed, definitively proving its extreme distance. Radio observations revealed energetic activity from its central black hole invisible in optical light. Perhaps the most pivotal development for studying distant galaxies was the launch of space telescopes. Earth's atmosphere, while essential for life, is a formidable barrier to astronomy. The atmosphere completely absorbs certain wavelengths of light blocking X-rays and much of the ultraviolet and infrared spectrum from ever-reaching ground-based telescopes. Even in visible light, the atmosphere shimmers and distorts, blurring images and limiting resolution. Space telescopes float majestically above all these problems. The Hubble Space Telescope, launched in 1990, was especially critical for studying galaxies like IC 1101. With its perch above the atmosphere, Hubble could capture images of astonishing sharpness, revealing details that would be smeared by atmospheric turbulence for ground-based observers. Hubble's observations of IC 1101 have allowed astronomers to study the galaxy's core in unprecedented detail. They have measured the size and brightness of the central region, compared the distribution of stars to theoretical models, and searched for signs of recent stellar activity. The 2017 study that precisely measured IC 1101's enormous core relied heavily on Hubble's exquisite data. Other space telescopes have also contributed. The Chandra X-ray Observatory has mapped the hot gas surrounding IC 1101, revealing the energetic environment in which this colossal galaxy resides. The Spitzer Space Telescope observed the galaxy in infrared light, detecting the glow of older, cooler stars that predominate in elliptical galaxies. Each telescope observing at different wavelengths adds another crucial piece to the cosmic puzzle. Ground-based telescopes have also dramatically improved. Modern observatories employ a technique called adaptive optics, which uses deformable mirrors and lasers to correct for atmospheric distortions in real time. The result is images that approach the quality of space observations, but from telescopes that can be far larger than anything we can launch into orbit. The largest ground-based telescopes today have mirrors over 9 meters in diameter, gathering immense amounts of light and capable of detecting objects billions of times fainter than the human eye can perceive. These instruments can observe IC 1101 with exquisite detail, measuring the motions of individual stars, analysing the chemical composition of different parts of the galaxy and tracking changes over time. Even more powerful telescopes are currently under construction. The James Webb Space Telescope, launched in late 2021, has already begun observing distant galaxies with unprecedented sensitivity in infrared light. The extremely large telescope, currently under construction in Chile, will boast a mirror nearly 40 meters in diameter when it first sees light in the late 2020s. These instruments will enable us to study IC 1101 and similar galaxies in even greater, more profound detail. There's also the fundamental question of how we measure distances to objects as remote as IC 1101. Distance is one of the most fundamental quantities in astronomy, yet it is also one of the most challenging to measure accurately. How do you definitively know how far away an object is when you cannot physically travel there and extend a tape measure? For relatively nearby objects, astronomers employ a technique called parallax. As Earth orbits the Sun, our viewing angle of nearby stars shifts ever so slightly. By precisely measuring how much a star appears to shift against the backdrop of more distant stars over the course of a year, astronomers can calculate its distance. This method works well for stars within a few thousand light years, but for more distant objects, the parallax shift is too minuscule to measure even with our most precise instruments. For more remote objects, astronomers rely on a cosmic distance ladder, a chain of techniques that build upon each other. One rung of this ladder involves a special type of star called a Cepheid variable. These stars pulsate regularly, varying in brightness in a predictable pattern, and their period of pulsation is directly related to their intrinsic luminosity, their true brightness. By measuring the apparent brightness of a Cepheid and its pulsation rate, astronomers can accurately calculate its distance. Cepheids can be observed in galaxies tens of millions of light years away. But IC 1101 is too distant even for this technique. At a distance of over 1 billion light-years, individual Cepheids are simply too faint to detect. For such truly immense distances, astronomers rely on even brighter standard candles. One of the most important of these is a type of exploding star called a type Ia supernova. These cataclysmic explosions occur when a white dwarf star accretes too much matter from a companion star and detonates in a thermonuclear runaway. Because the conditions for this explosion are remarkably similar, from one supernova to the next, they all reach approximately the same peak luminosity. By measuring the apparent brightness of a type Ia supernova, astronomers can estimate how far away its host galaxy is. Another crucial technique involves measuring the redshift of galactic light. As the universe expands, light from distant objects is stretched to longer wavelengths. This shifts the light towards the red end of the electromagnetic spectrum, hence the name redshift. The farther away an object is, the more the universe has expanded since its light was emitted, and the greater its redshift. By precisely measuring the redshift of light from IC 1101, astronomers have determined that it is approximately 1.04 billion light-years away. This measurement, combined with observations of the galaxy's apparent size and brightness, allows them to calculate its physical properties, such as its true diameter and stellar mass. Each of these techniques carries its own inherent uncertainties, and measuring cosmic distances is far from a simple, straightforward problem. Astronomers continually refine their methods using new observations and improved understandings of fundamental physics. The distance to IC 1101 may be refined with better data, but the fundamental picture of a colossal galaxy located over 1 billion light-years from Earth is firmly established. I also want to reflect on the profound implications of observing something 1 billion light-years away. When we gaze upon IC 1101, we are not seeing the galaxy as it exists right now, in the present cosmic moment. We are in a very real sense seeing it as it was over 1 billion years ago, when the light we detect today first began its arduous journey towards Earth. 1 billion years ago, Earth itself was a vastly different place. Complex animal life had yet to evolve. The planet was populated by single-celled organisms and perhaps rudimentary multicellular life, but nothing recognizable as animals or plants. The continents were in different positions, coalesced into configurations that would be unrecognizable today. The atmosphere had a different composition. It was an alien world by any measure. Throughout all that immense span of time, the light from IC 1101 has been relentlessly travelling through space. It traversed the vast cold void between galaxies, occasionally passing through tenuous intergalactic gas clouds, or being slightly bent by the gravity of intervening objects. It travelled at the fastest speed anything possibly can, yet the distance was so utterly immense that it took over 1 billion years to arrive. The IC 1101 we perceive in our telescopes today could be very different from the IC 1101 as it exists right now. Over 1 billion years, much could have changed. Stars that were shining then might have burned out by now. New stars could have formed. The central black hole might have undergone new feeding events or entered periods of dormancy. Galaxies that were falling towards IC 1101 1 billion years ago might have been consumed by now. We have no way of knowing what IC 1101 looks like at this very instant. Information about its current state will not reach us for another 1 billion years. In a very real sense, we are cosmic archaeologists studying the past rather than the present. Every observation of a distant object is a glimpse back in time, a snapshot of what was not what is. This inherent time delay is both a limitation and a profound opportunity. It limits our ability to understand the current state of the universe, but it allows us to study cosmic history directly by observing galaxies at different distances and therefore at different points in their past. Astronomers can painstakingly piece together how galaxies have changed over cosmic time. We can observe what galaxies looked like when the universe was young, compare them to more recent examples, and trace the evolution of cosmic structures over billions of years. IC 1101, viewed as it was 1 billion years ago, provides a crucial snapshot of a colossal galaxy at a specific stage in its evolution. Other giant elliptical galaxies, some closer and some further, provide additional snapshots. By combining all these observations, astronomers construct a cohesive dynamic picture of how these magnificent galaxies form and change over time. Now let me address something that I personally find deeply fascinating. The numbers we have discussed are so incredibly vast that they quickly become abstract. 100 trillion stars, 4 million light years, a billion years. These are numbers that our brains evolved to navigate a terrestrial world are poorly equipped to process. We are hardwired to count small groups to measure distances we can walk to, track the durations of seasons and generations. Nothing in our evolutionary history has prepared us for the mind-bending scale of the cosmos. So let me attempt a few more thought experiments to help make these numbers a little more visceral, a little more tangible. Imagine you wanted to take a photograph of every single star in IC 1101. You have an incredibly fast camera that can snap one picture every second, and you never ever need to rest. How long would it take you to photograph all 100 trillion stars? The answer is over 3 million years. If you had started taking pictures when the very first human-like hominids evolved, you would still have millions of years of photography ahead of you. Or consider this. The number of grains of sand on all the beaches of Earth is perhaps hundreds of trillions. IC 1101 contains roughly the same number of stars as the number of grains of sand on every beach across our entire planet. Each one of those stars is a nuclear furnace fusing hydrogen into helium, unleashing energy that radiates outwards in all directions. Each one could host planets. Each one has a story, a history, a future. Now imagine attempting to walk across IC 1101. The average human walking speed is about 5 kilometers per hour. At that relentless pace, walking 24 hours a day without stopping, you would require approximately 50 trillion years to walk from one side of IC 1101 to the other. That staggering number is over 3,000 times longer than the current age of the universe. You could walk for the entire history of everything that has ever happened, from the Big Bang until now, and you would have covered less than 3,000th of the distance across this single galaxy. Or think about communication. Light is the fastest thing in the universe, travelling at approximately 1 billion kilometers per hour. A message sent by light from one side of IC 1101 would take 4 to 6 million years to reach the other side. If a civilization on one edge of IC 1101 sent a message to a civilization on the other edge, the receiving civilization would not get the message for millions of years, and any reply would take millions more years to return. Communication across a single galaxy would stretch across geological timescales. These thought experiments don't truly make the numbers graspable. Nothing can. The human mind is simply not built for cosmic scales. But they can give us a sense of the immensity, a gut feeling, even if not a true intellectual understanding in our heads. Now let me pivot to a question that might be forming in your mind. If IC 1101 is so large, are there aliens living there? Could a galaxy containing 100 trillion stars possibly be home to intelligent life? This is the kind of question that science cannot directly answer right now. We have no means of detecting life in distant galaxies. We barely have the technology to search for life within our own solar system, let alone galaxies 1 billion light years away. But we can ponder what the numbers suggest. If life requires planets and planets orbit stars, then a galaxy with more stars inherently offers more potential homes for life. Our Milky Way might contain anywhere from 100 billion to 400 billion planets. If even a tiny fraction of those planets are suitable for life, then there could be millions of worlds teeming with living organisms within our galaxy alone. Extrapolate that to IC 1101 with its 100 trillion stars, and this galaxy could plausibly host hundreds of trillions of planets. Even if only 1 in 1 billion of those planets developed life, that would still mean hundreds of thousands of living worlds. Even if only 1 in 1 trillion planets developed intelligent life capable of building civilizations, that would still equate to 100 civilizations within IC 1101. Of course, these numbers are based on assumptions that we cannot currently verify. We do not know how common life is in the universe. We do not know how often life evolves intelligence. We do not even know for certain that life requires planets like ours, or needs water, or is carbon-based. The sheer diversity of conditions across the universe could be matched by an equally vast diversity of forms that life might take. What we can say is that IC 1101 provides an absolutely enormous canvas for whatever processes might lead to life. A galaxy of that size has been producing stars for billions of years. The heavy elements, carbon and oxygen and iron, that living organisms require have been produced in stellar cores and dispersed through supernovae countless times. Whatever the recipe for life might be, IC 1101 has had immense resources and colossal amounts of time to cook it up. And if intelligent life does indeed exist within IC 1101, what might they contemplate when they gaze up at their night sky? Their view would be profoundly different from ours, where we see a relatively sparse field of stars with a sweeping band of the Milky Way stretching across the heavens. They would perceive stars everywhere in every direction. The stellar density in an elliptical galaxy like IC 1101 is far, far higher than in the disk of a spiral galaxy like ours. Near the very centre of IC 1101, the night sky would be ablaze with light. Stars would be packed so incredibly close together that there might be no true darkness at all. The combined light of billions upon billions of nearby stars would fill the sky with an eternal twilight glow. Stellar navigation would be an impossible feat, as there would simply be too many stars to distinguish individual ones. Further out from the centre, conditions would be more akin to what we experience, yet still dramatically different. No sweeping spiral arms would etch patterns across the sky. No central band of light would mark the plane of a galactic disk. Instead, stars would be distributed in a more spherical randomized pattern, enveloping any observer in a shimmering blanket of starlight. Would such beings know about the history of their galaxy? Would they have discovered that their home was built from the remnants of dozens of smaller galaxies consumed over billions of years? Would they have detected the monstrous black hole at their galaxy's core, or figured out that their universe was billions of years old? We cannot know. But it is a fascinating thought that somewhere within IC 1101, on one of its hundreds of trillions of possible planets, intelligent beings might be asking the very same profound questions about the universe that we ask here on Earth. They might be looking out into the surrounding space, seeing other galaxy clusters far away, wondering if those distant specks of light harbour other minds. They might even have detected our Milky Way, though. From their perspective, it would appear as just another unremarkable spiral galaxy among billions. The universe is incomprehensibly vast, and the possibilities it contains are equally immense. Every galaxy we study reminds us of this immensity, and challenges us to contemplate our place within it. Now, I want to take some more time to explore the immediate environment surrounding IC 1101, because no galaxy exists in complete isolation. IC 1101 sits squarely at the centre of the Abell 2029 galaxy cluster, and understanding this cluster helps us comprehend why IC 1101 became so colossal in the first place. Galaxy clusters are among the largest gravitationally bound structures in the universe. They can contain hundreds or even thousands of individual galaxies all orbiting around a common centre of mass. The space between the galaxies within a cluster is not empty. It is filled with extremely hot gas heated to temperatures of tens of millions of degrees by the gravitational energy released as the cluster formed. Abell 2029 is what astronomers refer to as a relaxed cluster, meaning it has settled into a fairly stable configuration over billions of years. The galaxies within it have had time to sort themselves out, with the most massive galaxies sinking towards the centre due to a process called dynamical friction. As more massive objects move through a sea of smaller objects, they experience a type of drag force that slows them down and causes them to spiral inward. IC 1101 sits at the very bottom of this gravitational well in the densest part of the cluster, where galaxies are most tightly packed. This prime location is no accident. IC 1101 grew to its immense size precisely because it was in this privileged position. As other galaxies spiraled towards the cluster centre, they encountered IC 1101 and were absorbed. The same process that brought IC 1101 to the centre also provided it with a steady supply of victims to consume. The hot gas filling the cluster also plays a crucial role in IC 1101's evolution. This gas, known as the intracluster medium, is incredibly tenuous by normal standards. If you could scoop up a cubic metre of it you would find only a few atoms, but because there is so much of this gas spread across millions of light years, it adds up to an enormous amount of mass. This gas is so hot that it emits X-rays, which is how astronomers detect it. X-ray telescopes like NASA's Chandra Observatory have mapped the distribution of this hot gas in Abell 2029, revealing that it is concentrated around IC 1101 at the cluster's centre. The gas forms a kind of superhot atmosphere around the giant galaxy, a thin, shimmering haze of superheated particles stretching for millions of light years into space. The presence of this hot gas has significant implications for IC 1101's future. The hot gas could in principle cool over time, radiating away its energy in the form of X-rays. As it cools sufficiently, it could then fall into the central galaxy and potentially fuel new star formation. In some galaxy clusters, astronomers have observed immense flows of cooling gas, hundreds of solar masses per year streaming into the central galaxy. But in the case of IC 1101, something appears to be actively preventing this cooling gas from triggering a new burst of star formation. The leading theory is that the supermassive black hole at IC 1101's centre is responsible. As gas falls towards the black hole, some of it gets heated up and violently blown back out into the cluster. This creates a powerful feedback loop where the black hole regulates the gas supply, preventing too much gas from accumulating and forming stars. This is the signature of black hole feedback. Whenever too much gas begins to cool, energy from the core reheats it, throttling star formation and keeping the system in a long, uneasy equilibrium. There are distinct cavities within the hot gas around the galaxy, immense bubbles that have been inflated by the powerful jets of matter from the central black hole. These cavities are millions of light years in diameter, colossal voids carved out of the intracluster medium by the energy emanating from the black hole. This feedback mechanism is thought to be crucial for understanding why massive elliptical galaxies like IC 1101 are not forming stars today. Without the black hole regulating the gas supply, flows of cooling gas would provide enough material to trigger significant star formation. But the black hole acts as a cosmic thermostat, heating the gas whenever too much of it begins to cool, keeping the galaxy in a state of perpetual energetic equilibrium. The intricate interplay between galaxies, their central black holes, and the hot gas in galaxy clusters is one of the most active areas of research in modern astrophysics. Scientists are still teasing out the precise details of how this feedback operates, how it varies from cluster to cluster, and its implications for the long-term evolution of the universe's largest galaxies. Now let me take you through a definitive timeline of IC 1101's history, reconstructed to the best of our ability from observational data and theoretical models. This timeline spans billions of years and involves processes that are profoundly difficult to visualize, but understanding it helps us appreciate how this cosmic titan came into being. The story begins approximately 13 billion years ago, not long after the Big Bang itself. The universe at that epoch was radically different from what we perceive today. There were no galaxies yet, only vast diffuse clouds of hydrogen and helium gas remnants from the first few minutes of cosmic history. These clouds were not perfectly uniform. Some regions were slightly denser than others, and gravity inexorably began to pull these denser regions together. In the first few 100 million years, these denser regions collapsed to form the very first stars and the very first primordial galaxies. These embryonic galaxies were small, irregular agglomerations of stars, nothing like the grand spiral and elliptical galaxies we observe today. They formed in the densest parts of the cosmic web, the intricate network of filaments and knots that define the universe's large-scale structure. The region of space that would eventually become the Abell 2029 cluster is one of these dense regions. Many small galaxies formed there, and they immediately began to interact with each other. Mergers were common in the early universe as galaxies were closer together, and the cosmic web was more compact than it is today. One of those primordial galaxies, or more likely the merged product of several primordial galaxies, was the direct ancestor of IC 1101. We don't know precisely what this original primordial galaxy looked like, but it was probably a collection of a few billion stars, perhaps 100,000 light-years across, with a nascent growing black hole at its centre. Over the next few billion years, this primordial galaxy underwent merger after merger. Each time a smaller galaxy wandered too close, gravity inexorably captured it, and eventually absorbed it. Each merger added more stars and gas, and each merger fed the growing central black hole. The galaxy became progressively larger, and its location at the centre of a dense region guaranteed a steady supply of victims. By approximately 10 billion years ago, IC 1101's ancestor had likely already become a giant elliptical galaxy, having undergone dozens of major mergers. It was already one of the largest galaxies in its cosmic neighbourhood even then, though not yet as massive as it is today. The next few billion years saw continued growth, though, at a somewhat slower pace. The most intense period of galaxy formation was slowly drawing to a close across the universe. Star formation rates were declining as galaxies used up their gas supplies. Mergers became less frequent as the expansion of the universe pushed galaxies further apart. But IC 1101 was in a privileged position. The Abell 2029 cluster had grown and matured, and IC 1101 sat at its very core. Galaxies continued to fall towards the cluster centre due to the immense combined gravity of all the matter there. And as they arrived at the centre, they encountered IC 1101. During this phase, IC 1101 likely underwent another 20 or 30 major mergers, along with countless minor ones. Each merger increased its mass. Each merger stirred its stars. Each merger fed its already colossal black hole. By approximately 5 billion years ago, IC 1101 had grown to nearly its present size. It contained tens of trillions of stars sprawling across millions of light-years of space. Its black hole had swelled to tens of billions of solar masses, and it had essentially exhausted its readily available prey. The remaining galaxies in the cluster were either too far from the centre to be easily captured or locked in stable orbits that would take many billions more years to decay. IC 1101 had consumed most of what it could consume. Its days of rapid growth were largely over. What remains today is what we observe. A dying giant, still immense, still magnificent, but no longer actively growing. Its stars are old, its gas supply is depleted, its black hole is relatively quiescent, occasionally flaring up when a stray bit of gas wanders too close but mostly dormant. IC 1101 has reached a state of stable grandeur, slowly fading as its stars burn out one by one. This history is not unique to IC 1101. Many giant elliptical galaxies at the centres of clusters have similar stories, but IC 1101 represents an extreme case of galaxy that was in the right place at the right time to grow to truly exceptional proportions. Not the only giant in the universe, but one of the absolute largest we have found. As I bring us closer to the conclusion of this exploration, I want to reflect on what IC 1101 signifies for our understanding of the universe and our own place within it. The universe is profoundly hierarchical. Smaller things combine to create larger things. Atoms form stars, stars form galaxies, galaxies form clusters, clusters form superclusters. This hierarchical structure is one of the defining characteristics of the universe. We inhabit a direct consequence of how gravity operates over cosmic time. IC 1101 represents the upper limit of this hierarchy for individual galaxies. There may be larger structures in the universe, vast walls and filaments of galaxies stretching for hundreds of millions of light years. But when it comes to single objects bound by their own gravity, colossal galaxies like IC 1101 are about as large as they come. Understanding the limits of cosmic structure teaches us about the fundamental physics of the universe. The very fact that IC 1101 is about 4 to 6 million light-years across rather than a billion light-years across tells us something profound about how gravity and dark matter and cosmic expansion all balance each other. If any of these factors were slightly different, the largest galaxies might be far larger or far smaller than what we actually observe. In a sense, IC 1101 is a message from the universe about its own nature. By studying this colossal galaxy, we learn about the rules that govern everything from the tiniest atoms to the largest structures. We learn about how time and gravity and energy have shaped the cosmos over billions of years. There is also something deeply humbling about IC 1101. We tend to think of ourselves as important, our lives and our world as significant, and in many ways they are. But IC 1101 reminds us that the universe operates on scales that utterly dwarf anything in human experience. A galaxy with 100 trillion stars located a billion light-years away, utterly indifferent to our existence. We are specks on a speck orbiting a speck in a galaxy that is itself but a speck compared to the true giants of the cosmos. Yet somehow those specks have figured out that IC 1101 exists. We have measured it, studied it, understood it. We have placed it in context, traced its history back billions of years, and projected its future trillions of years hence. From our tiny perch on a rocky world around an ordinary star, we have reached out with our minds to comprehend objects of incomprehensible size and age. Let me share a few more thoughts on what IC 1101 teaches us about the nature of existence and our place within it. First, consider the profound improbability of our situation. For consciousness to emerge, a remarkable sequence of events was required. The Big Bang had to create matter with precise ratios. That matter had to coalesce into galaxies and stars. Stars had to create heavier elements in their cores and disperse them through supernovae. Planets had to form from those dispersed elements. On at least one of those planets, chemistry had to become sufficiently complex to produce self-replicating molecules. Those molecules had to evolve over billions of years into organisms capable of thought, curiosity, and scientific inquiry. Every step in this chain was dependent on the preceding ones. Had any of countless variables been even slightly different, we would not be here to contemplate IC 1101. The conditions allowing for intelligent observers to exist are astonishingly narrow, and the very fact that we exist at all is a kind of profound miracle. Now consider what we do with that existence. Of all the things humanity could choose to ponder, we choose to wonder about the stars. We construct colossal telescopes, launch satellites into orbit, dedicate careers to understanding objects we will never touch. We invest immense resources and effort into answering questions that have no immediate practical application. Why do we do this? I believe it is because there is something fundamental in human nature that needs to be understood. We are pattern-seeking, question-asking, meaning-making creatures. We cannot look at a mystery without wanting to unravel it. The existence of IC 1101, so vast and so distant, is perhaps the ultimate expression of the mysterious universe we inhabit. And our drive to understand it is perhaps the ultimate expression of what makes us human. There's a famous image called the Hubble Deep Field taken in 1995. The Hubble Space Telescope was pointed at a tiny, seemingly empty patch of sky, an area about the size of a grain of sand held at arm's length. It collected light from that patch for over 100 hours. What the image revealed was nothing short of astonishing. That tiny patch of sky contained roughly 3,000 galaxies, each one, an island universe containing billions of stars. Since then, even deeper images have been taken. The Hubble Ultra Deep Field, the Hubble Extreme Deep Field, and most recently images from the James Webb Space Telescope have revealed more and more galaxies in progressively smaller patches of sky. The conclusion is inescapable. Everywhere we look, no matter how small the patch of sky, we find galaxies. The universe is brimming with them, perhaps 2 trillion in total, stretching for billions of light years in every direction. IC 1101 is just one of those 2 trillion galaxies. It is a special galaxy, yes, larger and more massive than almost all the rest, but it is still just one galaxy among an unquantifiable multitude. The fact that we have singled it out, studied it, and understood it is a testament to human curiosity and ingenuity. But we could have chosen almost any galaxy and found equally remarkable wonders. The universe is generous with its marvels. I also want to reflect on the significance of knowing something about IC 1101 that no human knew just a few centuries ago. William Herschel, when he first glimpsed this object in 1790, could likely not have conceived of what he was seeing. He saw a faint fuzzy patch. We see 100 trillion stars, a 50 billion solar mass black hole, billions of years of cosmic history. The difference between his understanding and ours is almost as vast as the distance to IC 1101 itself. This progression in understanding did not happen automatically. It required countless individuals contributing their pieces to the puzzle. Astronomers built larger telescopes. Physicists developed theories of light and gravity. Engineers designed satellites and instruments. Mathematicians developed the tools to analyze the data. Each generation built upon the work of those who came before, slowly constructing the edifice of knowledge that allows us to comprehend objects a billion light-years away. When you think about IC 1101, you're not just thinking about a galaxy. You're participating in a tradition of inquiry that stretches back centuries. You're standing on the shoulders of giants, as Newton famously said, seeing further by the accumulated efforts of all who preceded you. The understanding of IC 1101 is not the property of any single individual. It belongs to all of humanity, a shared intellectual heritage that transcends any individual or nation. There is something deeply profound about democracy in this. Astronomical knowledge is available to anyone who wishes to learn. You don't need to be rich or powerful to learn about IC 1101. The information is there in books and papers and videos like this, waiting for anyone curious enough to seek it out. The universe reveals itself to anyone who asks. I find this thought incredibly encouraging. In a world that often seems divided and contentious, the pursuit of cosmic knowledge is something that unites us. It doesn't matter what country you come from, or what language you speak. The stars shine for everyone. And the truth about IC 1101 is the same truth everywhere. Science at its best is a collaborative endeavour that brings people together across all the boundaries that so often divide us. Let me also speak to something about awe. Throughout this exploration of IC 1101, I've tried to convey not just the facts, but also the feeling. The fact that IC 1101 is 4 to 6 million light-years across is interesting. The sense of awe that this fact evokes is something more than that. It is an experience, a state of mind, a way of interacting with the universe that transcends purely intellectual understanding. Awe is often dismissed as childish, something we are supposed to outgrow as we become serious adults with serious concerns. But I believe awe is essential for a well-lived life. It opens us up to experiences that go beyond our everyday routines. It reminds us that there is more to existence than our immediate problems and pleasures. It connects us to something vastly larger than ourselves. IC 1101 is an opportunity for awe if anything is. 100 trillion stars, 4 to 6 million light-years across a billion light-years of light travel a supermassive black hole, containing 50 billion solar masses. Numbers so large they defy comprehension. Distances so vast they beggar the imagination. If you can contemplate these things without feeling awe, I'm not sure what would move you. But awe does not require understanding. You can feel awe in the face of IC 1101 even if you don't grasp all the science behind it. The feeling of immensity, the confrontation with scales that transcend human experience, the recognition that there is so much that exists beyond our tiny world. These things are available to anyone who takes the time to truly ponder what we have discussed. Science enhances awe by revealing the specifics, but awe itself is a fundamental human reaction to the vastness of creation. That is the true magic of science and of astronomy in particular. It's not just the objects we study, magnificent though they are, but the very fact that we can study them. Consciousness, looking out at the universe and understanding what it sees. Matter, understanding itself. I want to leave you with one final thought. The atoms in your body were forged in stars. The carbon that makes up your muscles, the oxygen you breathe, the iron in your blood. All these elements were created in the nuclear furnaces at the cores of stars that lived and died before our sun was even born. When those ancient stars exploded in supernovae, they scattered their elemental treasures across space. Eventually, some of those atoms found their way into a cloud of gas and dust that collapsed to form our solar system. They became Earth, and after billions of years of evolution, they became you. You're made of star stuff. This is not poetry, it is chemistry. The very same processes that lit the 100 trillion stars of IC 1101 also created the matter that you are composed of. There is a direct physical connection between you and those distant fires. In a very real sense, when you contemplate IC 1101, you are star stuff contemplating more star stuff. The universe is looking at itself, trying to understand what it is and how it came to be. We are not separate from the universe we study. We are a part of it, and our curiosity is the universe curious about itself. IC 1101 will never know that we discovered it. Galaxies have no minds or experiences, but we know, and in knowing we complete a circuit that connects human consciousness to cosmic grandeur. We are small, yes, we are fleeting, yes, but in our brief moment of existence we can reach out across 1 billion light years and touch the largest galaxy ever discovered. That reach is our glory. When you next gaze up at the night sky, remember IC 1101. You cannot see it with your naked eye. It is too distant and too faint for human vision, but it is there in the direction of the constellation Virgo, shining with the light of 100 trillion stars. It has been there for billions of years, and it will remain there for billions more. Long after our sun has burned out, long after Earth has been consumed by an expanding red giant, IC 1101 will still be there, slowly fading into the cosmic night but not yet gone. We are a part of a universe that contains such wonders. We are made of the same matter as IC 1101's stars, forged by the same processes, governed by the same laws of physics. In studying that distant giant, we learn about ourselves and our place in the grand narrative of cosmic evolution. The largest galaxy we have ever discovered is larger than your imagination. But the very fact that you can imagine it, that you can hold in your mind a picture of 100 trillion stars stretching across millions of light years, that you can wonder about its past and its future and the beings that might inhabit it, that perhaps is the most astonishing thing of all. Thank you for joining me on this journey of discovery to the largest galaxy ever found. If this video has helped you see the universe in a new way, please leave a comment letting us know what you think about our place in a universe that contains such wonders. And if you want to continue exploring the mysteries of the cosmos with us, don't forget to like this video and subscribe to the channel. Until next time, keep looking up and keep wondering.